So thank you for the very kind introduction. So I will talk about bringing two things together, sustainability and AI, and I first talk about for understanding and then for forecasting. So let me give me just like one example of understanding. So this is like a car driving through the scene. You have a LiDAR sensor, what all the cars will have in the future. And what I see is like the observation of the environment. And the understanding, when I talk about understanding, means interpretation of the environment, and you see the different color, like what are the streets, where are the parking cars, where are children around them. And that's very important, right? Because we want to make the traffic, the driving more safe. Another application, what we also address, this is in the context of the excellence cluster FENEROP. It's in the domain of agriculture. So we go on the fields, either with smartphones, robots, or we fly with drones over the fields. And now we get kind of the image what you can see here. And we want to actually identify if there are any kind of nutrient deficiency. So we know it's very important because at the end we have a big issue with using too much fertilizers on our fields. But if you look at the images, so I give you two examples. We have two deficiencies. If a non-expert, including myself, I would not recognize if there's something missing or not. So this is kind of an application in the sustainability to reduce fertilizer. But the question is AI itself sustainable? And to let me give you kind of an idea, I show you a plot. What I see at the bottom is like the amount of images what you use for the pre-training. Just to make it clear, that's not a training on your original data set, that's just you do like a warm-up pre-training. And what you see is like the accuracy here on the axis goes up when you increase to roughly 300 million images. And you also know 300 million images processing, there you need HPC. And the size of the circle, this is different kind of networks. The bigger they are means they have more parameters. And the good news is, in some sense, that if we make our models bigger, so bigger size, more data, we get much more better results. And that's what we observe at the moment. But in terms of sustainability, it also means more energy consumption. Therefore, what we also address, how can we make this kind of the networks more efficient? And to illustrate it, how we actually do it, I show you two videos. You see on the right a video, very exciting video with very interesting personalities. Some are also here in the room. This actually has been taken from the Summerfest last year. And on the left, there's also a video. It's not an image, it's a video. You have a cat dozing away. If you look closely, the eyes are a little bit moving, some little movement at the ear. But the current way how we process data, we take the same amount of resources to understand both videos. But to understand the cat videos, as a human, we don't need even like a second. So now we actually want to do is, or what we have done, we actually make these networks more efficient to only use as much resources as needed to understand the content. And I give one example, which is like a transformer architecture. So transformer architecture, you can apply to any modalities. And what it actually does here in the bottom is you have an image, and you divide the image in small patches. So what you can actually see here. There are a lot of kind of operations happening in the encoder. I'm not talking about this one, but at the end you have a small head and you make a prediction. What is the probability that the image, for instance, contains a bird, a ball, or a car? So now comes the question, do we need all this kind of image information? And now what we actually did is like we modified this type of the networks that the network selects by itself what information I have to take in the image to make the correct prediction. And here you see some examples. So we have one image as an input image of a bird in the blue sky. And this is exactly the patches which have been selected by the network to make a correct prediction. So what it does is actually quite what we expect. So it takes this kind of the patches around the bird, and it also takes some patches in the background. And that's very intuitive, because at the end, a blue sky is a strong indicator if it's a bird or an airplane for a subset of the classes. And now the interesting part is like when we look at the cheese image, so we see like the image is a little bit more difficult. We probably would also need a little bit more time to recognize what's in it. And the same is actually happening with our network. So it selects more patches compared to the bird, but it's still interesting that the patches are focusing on the cheese and not on the shelf. So this is like a rough idea of what's going on, but what does it actually mean in terms of energy consumption? So to have HPC, I have at least one plot regarding G-flops, which measure like the amount of operation, what you need to do to make a prediction. And on the y-axis, like what is actually the image classification accuracy. And the only interesting part of this plot are the green arrows. because this gives me like an error and shows like we get a reduction of the computation operation by around 30% or more, but it's like aligned with the axis, so the accuracy does not change. So in other words, I can use this method without reducing the accuracy, but I change, roughly spoken, my energy consumption by 30% or more. And just a little bit make clear how brilliant this kind of approach is, it's the way how I can use it. Because it is as simple as mounting a water-saving shower head in your shower at home. That actually makes it very useful, easy to use, and saves a lot of energy. So, but what is like if I don't have enough data? Because we have seen we need a lot of data, and now I talk about the other task, what we ought to do, and you probably heard about is generative AI. So what we actually have here is like an image of like a semantic map. So each color corresponds to a different class. Red is like a bed, and we have a room layout, and now we have trained our network, which actually predicts images which are consistent with this layout. So this is some of examples. Given this a layout, it generates multiple images. And we can also say, well, we maybe like the room, but not the bed. So we can also say, please modify the bed. And you also get images with kind of different shapes of the bed, but still the room is the same. So generative AI is nice, but how does it actually help us for the understanding? And now I'm actually coming back to the task of image segmentation. So this is actually also here from Bonn. So Bonn doesn't have so many bridges, but it's one of the bridges over Bonn. And what I see is again the semantic labels, what are shown at the beginning. So the street, the cars, the pedestrians, and the cyclists. And one of the issues, if you want to understand the environment, one of the big problem is that the more rare the classes are, the difficult the task is. And this we can also see. So if you have like small cyclists, the probability that we can recognize is actually lower. We can also quantify it. So if you would sort the classes, looking at this kind of semantic classes, which occur in over 80% of the cases, we get a nice accuracy. If you look at the rare cases, but that's actually the important classes, then the accuracy goes down to 50%. So now what we can do, we can use generative AI to generate more variation of the rare cases. And now if we add this kind of part as part of the training, we see we get an improvement, and the main improvement is actually for the rare cases. And this is very useful. So now coming to the last part, and that's forecasting. We have seen also a little bit connected to the talk by Jürgen Gall before. There were devastating fires, wildfires in Greece, entire Europe. We will face this issue also more in Europe and in Germany, as well North Rhine-Westphalia. And then one of the tasks what we also have done is like we take observation like humidity, temperature, and now for Greece we predict for the next day what is the probability map that a new wildfire will start. So this is like an example. So we have it's like for the test, like all the data from 2021, July. This black circle, that's exactly in the records where a wildfire started. And the map, what is actually here, that has been predicted, so it's also nicely localized. It's not like everywhere red, what you have in a standard warning, what you have in your app, but it's really more localized where actually wildfire starts. And another example, in August, also 21, there were a lot of wildfires in Greece. Also here we see a large map, but also here where actually wildfire started, it actually has been predicted. So now coming to the last part, and then bringing the connection between AI and simulation, because when we make more longer forecasts, we do not want to forecast for the next day, for the next years, and also take the example of agriculture drought, which was introduced by Jürgen Gall in the previous talk. So we combine a simulation model and the deep learning approaches to do actually forecasting in years ahead where actually we can expect agriculture droughts. There are different ways how you measure them, but one of the kind of the indices which actually will be combined is looking at the vegetation, and you look a little bit kind of like a vegetation health index which combines this kind of indices, and red means like that's an indicator where we expect stress for plants because of droughts. To a little bit to see how well our predictions are, we can compare with remote sensing data and that which has been predicted, so we stopped the observation 2 years before. And if we look at this kind of the data in Europe, we see that there's actually quite consistency between the prediction, even the time horizon is like 2 years ahead of time. So now coming to the summary slide already, because everyone I think wants to press the red or see the red button is pressed. I think I a little bit give an indicator that actually AI is nowadays a versatile tool for science. And when I talk about science, I mean any science. And this is also why we actually need Marvin, and also looking forward for Marvin 2. We have seen we need more data, the models getting larger, but we cannot do this kind of research without having these resources. So Marvin is not only very important for Bonn, but also for North Rhine-Westphalia and the entire landscape. So this brings me to the end, and I hand over to Petra.